front of me, and thank you for coming, the people who are sitting somewhere on the internet. It gives me great pleasure to welcome Kumar Venayagamoorthy. Okay. I remember these rumors when I was doing my physics, studies in physics department, and I heard these rumors about this brilliant student called Kumar, and he was a PhD student of the late Ron Harley. Unfortunately, he left South African shores. Like all these guys leave South African shores to become amazing people. Land and opportunity. Anyway, okay, so it gives me great pleasure to welcome Kumar. And today's talk is titled Distributed Artificial Intelligence in Smart Grids. Okay. Just to formalize the process, I'd like to introduce Kumar formally. Okay, so he is the Duke Energy Distinguished Professor of Power Engineering and Professor of Electrical Computer Engineering at Clemson University since January 2012. If I recall, we also lost another professor to Clemson University. Anyway. Prior to that, he was Professor of Electrical and Computer Engineering at Missouri University of Science and Technology in the US, where he was there from 2002 to 2011. He was a senior lecturer in the Department of Electronic Engineering at Durban University of Technology, where he was there from 1996 to 2002. When he was there, he was BTech and MTech Program Coordinator for Electronic Engineering Department and Chair of the Faculty of Engineering Research Committee. Kumar is the founder and director of the Real-Time Power and Intelligence System Laboratory at Missouri Science and Technology at Clemson University. As I alluded to previously, he received his PhD and MSc engineering degree in electrical engineering from the University of Natal, Durban, South Africa, between 2002. Is it around about there? Yeah, that makes sense. The rumors were percolating down the road. Okay, he also holds an MBA degree in entrepreneurship and innovation from Clemson University. Kumar's interests are in research, development, and innovation of smart grid and artificial intelligence technologies. He's received a number of prestigious awards and led, to name a few, and led the Brain to Grid project funded by the US National Science Foundation. He's also inventor of technologies for scalable computational intelligence of complex systems and dynamic stochastic optimal power flow. This is the one that just freaks me out. He's published over 550 referee technical articles and cited 21,000 times. It's an H index of 70. Okay, I'll never be there. Okay, and an H10 index of greater than 290. Okay. He is involved in the leadership and organization of conferences, including Clemson University Power System Conference, and pioneer and chair and co-chair of the IEEE Symposium of Computational Intelligence Applications in Smart Grid since 2011. He is currently the chair of the IEEE PES Working Group of Intelligent Control Systems and the founder and chair of IEEE Computational Intelligence Society Task Force on Smart Grid. He has served and serves as editor, associate editor, guest editor of several IEEE transactions and Elsevier journals. He is editor of the IEEE Press Series on Power and Energy Systems. Kumar is a fellow of the IEEE IET UK, the South African Institute of Electrical Engineers, and Asia Pacific Artificial Intelligence Association, and a senior member of the International Neural Network Society, according to According to Elsevier, Kumar has been ranked in 2019, 2020, and 2021 as among the top 25 scientists worldwide across all fields, and it is in the top 0.1% worldwide in the and control. AI has evolved over the last 40 years to transform operations and control of complex systems. A smart grid with variable power and energy sources, bidirectional power flows, and uncertainty in forecasting and real-time availability of generation, loads, energy storage, and other operational resources require distributed intelligence and computational technologies for its operation and control. Examples of such technologies include AI for stable, secure, reliable, and efficient operations, and control for smart grid will be presented. Thank you very much. I'd like to welcome Kumar.
Thank you for that introduction, and sorry it was a bit long. So it's thank you again for the invitation to come back to UKZN. It's always nice to be here. My home institution, where I actually learned how to do research, taught by late Professor Ron Harley, who I dearly miss, and who I have had a long journey with, not only as an advisor, but also as a friend and colleague. After my PhD, we spent about 15 years working together on a number of research projects as colleagues while I was at Missouri and at Clemson. So whenever I come back to UKZN, I always think of my first meeting with Ron Harley back in 1994. I think I met him in October 1994. Before that, Ron Lee was here. I don't know how many of you remember Ron Lee. He was a lecturer, but he is the one who was admitting students. And so I first met him in, I think, May of 1994. So it always reminds me of those days when I come back here. And so this morning, I have titled my presentation as Distributed AI in Smart Grids. Of course, I started working with Ron Harley on neural networks. I think Ron Harley was one of those pioneers. I think Lee Jarvis knows about Bruce Burton. Back in 94, 96, those time when Ron Harley worked on induction machines where neural networks were implemented. So that's when I started my journey in AI. But today, we have hit saturation, just like in the traditional power systems. Now it's smart grid. Also in artificial intelligence, it's not just artificial intelligence, but it's now, we have to think about there's saturation in artificial intelligence too. Of course, everybody is gets on the wagon of AI, but AI is also hitting saturation. And the next step in AI is, how do you realize AI in a distributed way? So my title, Distributed AI in Smart Grid. Yeah. So the outline, I'll give a brief, quick introduction, and then I will take us through distributed AI. How do we realize distributed AI and the need for distributed AI? Then I will just, there are a number of case studies I could present, but I've chosen 3 case studies: a microgrid, dynamic energy management system, power system modeling, and cyber attack. So 3 different problems. But I could present a dozen problems and we would be here till tomorrow, but I don't want to do that. So, but you're welcome to communicate with me later on if you have a particular topic and how some of these technologies can be applied. I'll be glad to talk to any one of you. Then I'll summarize my presentation. So I always talk about the 2003 blackout because it's a very good example of how the traditional power system collapsed in the United States, the North American power system, which is known as the single largest machine ever built by man, and it still stands today. Of course, maybe the internet now is overtaken. Over 60 gigawatts of load lost during that blackout, more than 50 million people affected. And after every blackout, there is a task force that looks at why the blackout happened. And the very simple conclusion is that there was inadequate situational awareness in the control centers. The system operators helplessly just watched the grid collapse in a few minutes. SCADA is the technology being utilized at that time, and even today, most of it is still SCADA. And SCADA data comes in at 2 seconds to 6 seconds. And many of these things were happening so fast that it was very difficult or almost impossible for system operators to comprehend what was going on, to be able to take any decisions and implement that in that short period of time with cascaded events happening. So at that time in 2003, we didn't have much of phasor measurement unit, synchrophasor technology in the US grid. Now we have over 4,500 PMUs. These PMUs are streaming data at 30 hertz, 30 samples per second. So you can imagine with the 3 interconnection, the eastern interconnection, the western interconnection, and the ERCOT, the Texas in the United States, it's very difficult to process 4,500 PMUs at 30 hertz and still for the human system operators to make sense. So lots of data, right? So this is where we need machines, intelligence to process this data, turn them into information, and information into knowledge, and then into understanding, and help the system operators with recommendation and even autonomous, semi-autonomous systems to make decisions. Today with that data, it's just monitoring that's possible. Closed loop control is still not yet there, which, there's a lot of value in this data, but how do you make sense of that data is the problem. So as we all know, the grid is very complex, and it's growing to be even more complex with the integration of renewables. There are uncertainties in the renewables, the variability and so forth, and also the load growing and having different types of load. And now we have electric vehicles, we have demand response. So load forecasting is not the same anymore if we consider the new kinds of loads. So it makes the grid even more complex than what it is, right? So of course, one can design control systems and optimization methods to try to ensure the grid operates efficiently, but it's very difficult because the grid is highly nonlinear, right? You can come up with linearized models. You can say you can design robust controllers, but when it comes to practical implementation of such advanced controllers, it's actually difficult. H infinity based controller, it's going to be hard to implement that. Still, the state of the art is PI controllers been implemented, linearized around some operating conditions, and those operating conditions no longer hold because of the vast variability that we have in the grid operations and the uncertainty. And when you think about integrating renewables, wind and solar, then this operating conditions even further change, right? So you can't say that you're going to design a PI controller to handle all these different operating. So you need some kind of intelligence to really track these operating conditions and have the best control possible. So when you look at the problem with the new evolving grid, it only makes sense to look at data-driven approaches. Data-driven approaches where data from IoT, Internet of Things, sensors, and actuators can be utilized. And of course, humans are good at analyzing data and making some decisions only when the data is of small size. When the data size grows big data, then we have to look at computers and human-like intelligence to be able to analyze the data, right? And this is what leads us to artificial intelligence. Of course, the other problem we have besides the data problem and the grid being evolving, the complexity in the grid evolving, is the climate emergency. Okay, I think we all have seen and witnessed now that the climate is different than what it used to be. We know today's weather is different than what it used to be 20 years ago. So much unpredictability and uncertainty. So looking at how we address the climate and the emissions, that of course we probably most of us here agree that the energy consumption, whether it is the electricity and also energy from the transportation, basically contributes majority of the emissions that we have today. 2/3 of this have happened in the last 30 years, 2/3 of the emissions. And that's because of the amount of energy we consume, right? So the only way to really achieve climate neutrality is to look at how we can stop putting out emissions from the energy, the ways in which we're consuming the energy, and look at new ways. And of course, we have to look at transformative technology revolution. And I strongly believe that smart grid is one to do that. Okay, so I think those people that are working in smart grid are not only going to be able to address how to come up with optimal solutions to handling the smart grid operations, but also how we can address climate emergency by innovative technologies for energy consumption, energy generation, and so forth. So this is not a new slide, and some of you might have seen this from my presentation. What is the smart grid? Right? Smart grid is basically modernization of the electric power system such that it has some basic functions. And this includes self-healing capability, being fault tolerant to attacks, able to dynamically integrate all forms of energy generation, whether it is wind, solar, all kinds of different energy mix, storage, even electric vehicles that can perform not only discharging from the grid, but also discharging to the grid, which we say vehicle to grid technology, right? Because that would be like emergency power that the grid need, or ancillary services that electric vehicles can provide while they are stationary. The dynamic optimization of grid operations and resources, because the grid is going to be highly dynamic, and optimization methods have to be now not static, but dynamic, right? Static optimization would mean that you optimize the grid operations every 15 minutes, and then you just hold those set points for that time period. But the grid is not static anymore. So you can't say that 15 minutes window is optimal. So you need to have dynamic optimization when the grid operations exceed a threshold, you trigger the optimization. So that kind of technology is what the grid would need. Demand response is going to be something that the utilities or the grid operation will become highly dependent on. Demand response is an asset of high value, if I may use that. It's a virtual asset, okay? So we have to capitalize on demand and how to have demand response to support grid efficiency, grid security, and so forth. And then, of course, electricity customers will now become electricity clients, okay? Because they will be prosumers. They not only will be consuming, but they can also produce. If all the consumers end up having rooftop PV, they become producers. So there'll be times in which the energy produced by the consumers will be exported to the grid, right? So now they're clients, they're no more consumers. Okay, so we have to give them that upgrade status and say now we are buying energy from them. So there'll be mechanisms to do this, implement such technologies on the grid. Overall, still we have to maintain and improve the grid reliability, the power quality, security, and efficiency. None of this can be compromised. So when you look at this 7 bullets here of saying basic functions for modernizing the grid, it looks like a dream intelligent machine. Okay? This act was put together in 2007 in the US, Energy Independence and Security Act. We are 15 years down the line now, and still we are far from realizing this basic functions in the grid yet. Okay, so it's a journey, but I think in a step-by-step manner, we can get there. Okay, it's easier to bring some of those functions into a grid on an island compared to the United States grid, which is a 50, 60 years old legacy system, right? The transition is there. So besides the physical power system or the smart grid, which have all the different renewables and IoTs, PMUs, microgrids, electric vehicle parking lots that can charge and discharge, all that physical system. But you also need the cyber system, right? That's where the computation takes place. That's where the thinking happens, the planning happens in near real-time planning, and all the iterations, convergence takes place before you actually do the dispatch, right? System operators spend a lot of time doing planning dispatch, right? But now, instead of system operators, we need intelligent machines to do this dispatch calculations that will be optimal. So we have the real power flows on the real system where once it's all implemented and dispatched, but then we have in the cyber, we have all this data coming in, all kinds of data signals, both at the transmission and the distribution. Of course, as time goes on, the T and D becomes gray. There's not much of a difference between transmission and distribution. Distribution will impact transmission. So sense making has to take place. And then, of course, some projections and predictions, situational intelligence, and human will be still involved, some visualizations that can connect with the system operators, and then decisions have to be made, and then eventually intelligent control based on the physical operating constraints. The cyber power flows have to be subject to the physical constraints, then it has to be dispatched. So we are dealing in this case with a lot of data. And again, I make the case for data-driven methods for both modeling, control, and optimization. And when you think about data-driven methods, then AI fits quite well for data-driven approaches. Of course, there's lots of challenges in the smart grid. Just to highlight some of them, we are dealing with distributed resources. As we move forward, more of distributed energy resources and loads. And the impact of the smart grid can be viewed. Let's say we realize all those 7 bullets. The impact can be viewed as how PCs have changed our life compared to when we used mainframe computing, right? How cell phones have changed. I think is it my echo coming back somewhere? Okay, all right. I hear my voice from there, so I'm wondering, is there a clone of mine back there? So cell phones, how cell phones have changed our lives compared to when we had landlines at homes, and life with and without internet. So today, a lot of folks are online and able to listen to this talk. Without internet, that would not be possible. Now we can be all over the world. Virtual presence is possible. So smart grid will change the way, if those 7 bullets can be realized and they're implemented, then smart grid will be so different. Digital energy compared to the kind of grid that we have today. Of course, to do this, sensing and communication will be highly relevant, and high-tech technology will be needed in that area to enable a digital power system. Of course, security, cybersecurity will be key because it will be highly vulnerable to attacks. And when you think about electricity markets, the business models will be so different that you will have multiple options, multiple paths, so many different applications running with dynamic interfaces. So you can think about the electricity market here. In the US, we recently introduced the FERC 2222, which allows retail market. Okay, so you and I, through an aggregator, can participate in the market, electricity market. So demand response will be part of that. So the opportunities will be vast, but of course, challenges are also goes along in hand with that. So for us to realize a secure, reliable, and a greener grid, different modeling, optimization, and control techniques are needed. And this would be multi-objective problems. They be dynamic. They have to be solved in a parallel and coordinated manner. And many of these things have to be solved ahead of real time, faster than real time. So we can't wait till something happens before we say, let's solve that. So lots of predictions have to be there, what the weather is going to be, how is that going to impact the wind power production, the solar power production, how is the loads going to change, all that has to be known on multi-time scale. You can predict that days ahead, you can predict that 24 hours ahead, and a few hours ahead, few minutes ahead, and you solve on multiple time horizons. And so I think those in system operations understand that you solve this in different time scales, and near real time also you have to solve that. So all of this have to converge, right? That's the key thing, right? Convergence is important. So when you think about this kind of technology that will be needed, multi-objective, dynamic, parallel, coordinated, faster than real time, then we ask ourselves, where does such technology reside? Where do we find something like that? And definitely each of us have a brain, and we do this all the time. We do multi-objective optimization. We are dynamic, right? And we do things parallel, multiple things. We do them in coordinated, and we are thinking our next steps, right? The problem with the brain is that it is slow, right? But it does all of these things, but it doesn't do it as fast as what is needed for the grid, right? So then if you think about what Einstein said, the best intelligence is in the human brain, but the fastest processing time is on the silicon. So if you combine the brain and the silicon, you can get both the speed as well as intelligence. So you have high speed intelligence, right? And then that basically tells us that we need to implement AI on fast processing silicon chips, microprocessors, microcontrollers, right? So that takes me to distributed AI. And I've already talked about situational intelligence of how data needs to be used to project. And situational intelligence is basically looking ahead how situations will unfold over time, immersing ourselves, looking into the future, immersion into the future, right? And you solve dynamic problems, you have so many trajectories. And every trajectory depends on what you decide as the next few decision points. From that, you can have different trajectories. So you can get into a lot of different trajectories, right? So there's so many paths you can take. And especially if you're going to solve for optimal power flow with all kinds of variable generation that has a lot of uncertainty, and you're looking for the best optimal solution based on some multi-objective cost function, you'll have several trajectories that you can solve. And one would ideally like to know what is the best trajectory? Where is the maximum yield? If I was a utility, I would want to know where I can still maximize my revenue, right, my profits, while ensuring not compromising on reliability, security, and efficiency of the operation. So situational intelligence helps us to do that. So which means we can do faster than real-time simulation to be able to find that optimal dispatch. Okay. And today we can't complain. Today we have high performance computing, GPUs, graphic processing units, and we can have a cluster of that and really solve many of these things, projecting into multiple time scales. So situational intelligence, SI, is different than situational awareness. Situational awareness is when we get the data from the IoT, the sensor, and then we say, this is the data, and we analyze, and then we try to solve for that. Situational intelligence is predicting what your sensor would produce at t plus time delta t. So what that delta t could be in seconds, minutes. What would that variable be at a time not yet there yet? Okay. So prediction. So predictive senses. Okay. So we basically can take a PMU, for example, a phasor measurement unit that puts out voltage phases and current phases, and now we can have this prediction algorithm that sits inside the PMU, and now you have not only the voltage and current phases at time t, but also at a time t plus delta t. So you make that PMU box more valuable, because not only it is telling you the current measurement, it's not just a measurement device, but also it's telling you, it has some intelligence, and it will tell you what that waveform will look like a few cycles ahead. Right. So, and none of the manufacturers have taken that yet from the PM, for those that are doing manufacturing PMUs. But it's easy to put a predictive algorithm in and put it on a chip and just connect it to, put it in the box there, and then you have this extra outputs that say this is predicted voltage and current waveforms. All right. And then you can use that to all kinds in operations, and you can make that value of that PMU much better, more than what it is today. So how do we do those predictions? How do we bring this intelligence? And I go back to CI, computational intelligence. Computational intelligence is basically part of AI. Machine learning is also part of AI. Everything comes under the umbrella of AI. Computational intelligence paradigms could be neural networks, could be fuzzy systems, swarm intelligence, evolutionary approaches, artificial immune systems. All this can be used basically to create computational models and tools of intelligence that can work on process numerical sensory data from IoTs, and come up with representational parallelism, pipelining the problem, all to generate just-in-time responses and that are highly fault-tolerant. Let me just take a minute here and talk about some of these paradigms. If we think about the biological systems, the two most critical systems for us is the nervous system and the immune system. If any one of the system collapse for one or more reasons, then basically we turn into a vegetable state, right? So the neural networks is inspired by the biological nervous system, or the biological neural system. And the artificial immune systems is inspired by the biological immune systems. And the whole idea of the neural networks is taking input and output. We can do some mapping and identify a nonlinear function that connects the output to the input. So dealing with a lot of data in the power system, and given that we have to solve this on multiple time scales, and there's so many trajectories one has to solve, we can use AI methods such as neural network to do what is known in the computer engineering field today as approximate computing. Right? Approximate computing does not get into solving, for example, when we do power flow, when we solve for power flow, optimal power flow and power flow, we solve differential algebraic equations. But instead of doing that, we can get that, instead of calculating the Jacobian, we can now use a neural network which implements that in an approximate way and gives us many more power flows that we can solve in the same time. So we can solve 10,000 power flows in minutes or within a minute. That's better than trying to solve 100 power flows in 5 minutes. Okay, so those are the methods that one has to look at, and neural networks can do that. Artificial immune systems can also be used to engineer solutions that have fault tolerance, right? Just like the biological immune system, the immunity basically gives us to handle different kinds of virus to different levels of degrees that we can. So artificial immune systems, basically, let's say you have a controller, and that controller was designed for X number of operating conditions, typical operating conditions during a 24-hour period. Now, if there's some deviations from those operating conditions, the artificial immune system can be designed to change the parameters of the controller by some delta based on the deviation delta that we have, right? So, and then when that deviations can be for a short time, is temporary. And when those deviations fall out, disappear, the controller reverts back to its default, right? So just like our immune system, when we subject to some disturbances in the environment, our immune system basically kicks in. There's adaptive immunity, and when that disturbance, that virus disappears, the immune systems will turn back to its innate. And in fact, the immune system would have learned this new virus that it would have now developed innate immunity. So we can also have learning where if this disturbance is happening periodically, the controller can learn that, and now it improves its robustness. So those mechanisms can be brought in. It can be engineered. Fuzzy systems basically allows us when we don't need really, in many cases, we don't need precise measurements. We only need to know gradients, right? When we know the gradients, then we can work with gradients to make decisions, which could result in a faster solution and prevent an emerging phenomena happening on the grid. Like an oscillation is trying to come up, you can use a fuzzy system to move away from that by changing the control. So you don't need to know exact things all the time. So fuzzy helps with that. So combining some of these technologies can really design intelligent tools, intelligent controllers, intelligent systems for the grid. Okay, so let me move on in the interest of time. So how do you bring all of this to basically build what I call as the computational systems thinking machine? And of course, the most important parameters of this CSTM, or the strands of thinking, is the sense making, decision making, and adaptation. So any controller you design that you want it to be conscious, intelligent, has to have these three things. It has to be able to make sense. That means understanding. Then using that to make the right decisions. And after making the right decisions, it doesn't stop there. From the decision, you have to implement it, closed loop, right, to the physical system. Keep in mind, sense making and decision making is in the cyberspace. Adaptation is when you actually go to the physical system, right? So at that point in time, the decisions that you you may have, with solutions you may have, may not all fit to the physical system. There are physical constraints. At that point, you make some adjustment, right? And when you go to real time with actual systems, so adaptation. So you need to have this in the middle of this three is the real-time wealth of knowledge, which is the model. Okay, I say real-time wealth of knowledge because real-time means it has to be current. It can't be out of date. It can't be an outdated model. It has to be current with the current situation on ground. And wealth means richness. Okay, the model has to be rich to the kind of problem you're solving. Okay, so the context is important. And this model has to continuously be refined, continuous refinement. And I also say that the model has to learn, not only learn, but also unlearn. There are certain things that may not be needed anymore, but the model has to shed them. So continuous refinement, learning and unlearning actively. So it is very key to have a good model. A good model means you have good awareness, good consciousness of what's happening on the grid. And this is key to advanced analytics for the grid. So brain-like intelligence, I already said the brain is the one that has all these different things that we need for the grid, multi-objective, basically able to solve, deal with large number of variables in parallel. And the technology or the tool, the method that exists for that is known as adaptive critic designs. It goes back to approximate dynamic programming. Dynamic programming, Richard Wellman's equation of dynamic programming, but here we talk about approximate dynamic programming because we know the problem with dynamic programming, the curse of dimensionality problem. We can't solve that. It's a backward method, but approximate dynamic programming is you can use data-driven methods to learn the cost to go function in an incremental way, and use reinforcement learning that uses gradients rather than precise scalar quantities. And real-time derivatives are very powerful because rather than having scalar feedback, if you have derivative feedbacks, they help to minimize the error signals. And of course, we can use neural networks as tools to get these real-time derivatives. And neural networks are not only just used to learn input-output mapping, but you use them as sense-making tools to get these gradients. Okay? And then you can solve optimal control problems in a dynamic way. So whether it is the power system, whether it is a stock market, whether it's a transportation system, all these are complex systems. You can use this kind of methods, the actor-critic method. Critic is the one that approximates the cost to go function. It's a forward projection of your actions and what it turns out to be as cost, not only at time t, but looking into the future, which helps you to design optimal control policies done by the actor. So I think all of us know that any action we take today has ripple effect into the future. And that ripple can be quite a bit, or can be quite small, depending on what it is. So the actor can foresee that, can get that feedback through the critic, and then helps control. Power system is not something that it's not like a bang control you can do on the power system. It's not on and off. It's not like turning the light on and off. Whatever controls you do has a ripple effect on the power system operations. So knowing this cost to go function into the future helps design the optimal control policy for the grid. So the model will be critical in that. And this is an architecture that one can use for both for controlling, for optimization and scheduling, all this power system operations. So I've talked about the technologies, but then I mentioned in the very beginning that AI is hitting saturation. So how do we go forward with distributed AI? Because scalability becomes a problem with AI. The power system is a massive system, many variables to deal with on the input side and output side. So data-driven approaches, AI methods, if you think about a neural network, how many inputs can you have? How many outputs can you have? And can you, how do you implement a neural network on the Eastern interconnection, for example? It's a nightmare when you think about that. And then you say, oh, no, it can't work. I'd like to introduce you to cellular computational networks. Some of you may have already read about this, where computational units are basically put together and they connect with each other in a distributed manner. Like, for example, here, each of this is a cell, and together it's a CCN, cellular computational network. Each cell has a computational unit. And this computational unit could be a time series algorithm, y a function of x, or it could be a neural network where y is a function of x1, x2, x3. That function is modeled by a neural network. It could be a fuzzy system. It could be any mathematical algorithm that sits inside the computational unit. There's an input x and an output y. And y is related to x by some function that has some coefficients. If it's a neural network, it's the weights of the neural network. And then we have a learning unit that makes sure that y is equal to x is current all the time. Remember the real-time wealth of knowledge, the model I talked about? So the learning unit makes sure that the computational unit exactly models the system or subsystem or component. And of course, the power system is many components, many subsystems, and you need the cell to handshake with other cells. Components, buses are connected to transmission lines, and in the substation, you have so many different components, and then variables are exchanged, so that you eventually have a 50 hertz frequency and whatever voltage that you're looking for at the respective buses. It's all harmonized and it's correct. So you need that communication unit. So that's what a cell is made up of. And that's what we do here. Right, this is a 10,000 bus power system in the United States, where we use the CCN to cluster the grid. This is the COVID, Italian, the COVID that happened in Italy. And there are 7 different political, I think, if I'm right, 7 different groups that had different views of COVID that was modeled using the CCN. Okay, so CCN can be used to model different things, whether it's a power grid, but it's a complex system, okay? The nice thing about the CCN is that it breaks down the complex systems into subsystems and components and cells. It's a distributed way of modeling. And the other thing is that you can have asynchronous learning in the cells, which means that if you have 4 cells, for example, and one cell doesn't meet its threshold performance, that cell can trigger its learning. So if you think about a large neural network having 100 inputs and 100 outputs, and if one of the outputs doesn't meet its threshold performance, you have to retrain the whole neural network. That's what happens with deep learning. I'm sure many of you are familiar with deep learning. And deep learning is quite brittle because once the data in the input-output functions changes from what it has learned, you have to retrain it. And retraining deep neural networks takes a lot of time, right? Depending on how much data you have, and also a lot of power to actually power the computing machine to learn that data. Okay, so it's not sustainable AI when you think about deep learning. Whereas with the CCN, I say it's shallow learning because only the cell that does not meet the threshold performance needs to be trained. Asynchronous learning. Okay, so not every cell have to learn at the same time. Okay, so you can have that in a distributed way. For example, to bring this home, if you take the South African Eskom grid, power grid here, if there's some change in the load profile in Durban, it doesn't have to affect the performance of the different regions of South Africa. In Gauteng, it may not. What happens in KwaZulu-Natal or Durban does not have to. You just have to update the cell that belongs to Durban, right? So you basically take the whole entire South African power grid and distribute it in a number of cells, and only the cell you can localize the problem while it's still connected to the rest of the network, CCM, because it's a network, right? And you can update the model. And even if you have to island part of the system, you're only islanding a cell in your model. So it becomes very flexible in the cyber space, because these things will happen anyway. You will have things fall out or things expand, and it's much easier to work with a CCN model of a complex system rather than just one large deep neural network model. So the way to realize the distributed intelligence will be, I've already told you about the CSTM, I've told you about the CCN, I've told you about the adaptive critic design. To bring all these pieces of puzzle together and have multiple CSTMs, one CSTM for Durban, one CSTM for Johannesburg, one CSTM for Cape Town, East London. Every city can have its own CSTM. And all of this is still connected because it's still one grid, one network, right? And the nice thing is that if you think about the CCN, inside each cell, the computational algorithm can be anything you want it to be. It can be a neural network. It can be just a differential algebraic equation, the traditional method. So in fact, you can take the traditional way of solving the mathematical algorithms and put it into the CCN framework. And now you have a distributed model and a distributed control, just using the same algorithms. And then you can move it into AI, data-driven, which works well. Okay, so I think that is distributed intelligence benefits and promises. We have all these different things that you can do. And the most important one is it's highly scalable. Okay. All right, so let me go through some case studies. How much more time do we have? And so that I can plan. I know I wanted to go through the first two parts to have a good understanding, because there are quite a few people online as well. Okay. All right, good. All right, so I'll go through 3 case studies to show the benefits of the methods that I've talked about. The first one will be the microgrid dynamic energy management system. So here we have a hypothetical microgrid that will have wind, solar, some energy storage, some backup generation, still connected to the utility grid, and the loads put into 2 categories. Loads that have to be powered all the time, critical load, classified as critical load, and loads that can go under load shedding or can demand response, non-critical load. So the 2 bins types of loads here. So we have a dynamic energy management system, and of course we are doing a lot of monitoring, situational awareness of all the states. Through some sensors, we get this states monitored. And the goal of the DEMS is to make sure it provides dispatches to how much of the critical demand it has to supply, how much of the non-critical demand it has to supply, how much of battery discharge, or what's the flow on the battery, and then how much to import from the utility grid, how much maybe to export to the utility grid, and how much from the diesel generator. It's basically power balance here. Of course, the microgrid operator or the owner will have some objectives and also wants to know how well is the DEMS carrying out, solving those objectives. So there's a performance index measure. The whole idea is the DEMS has to maximize the performance index while meeting all the objectives, right? The energy storage can also be electric vehicles, right? So now electric vehicles are coming more and more on the road and in the parking lots, and then we can create a smart park where we have electric vehicles that can do charging and discharging. G2V, grid to vehicle charging, and then vehicle to grid discharging, right? So that is a smart part. So you can realize this energy storage either with some fixed energy storage and also mobile energy storage from the vehicles as well. The objectives of the energy management system, let's say an intelligent energy management system, IDENS, can be as follows. Of course, the critical load has to be met all the time, so 100% supply to the critical load. You want to ensure that the battery state of charge is at the optimal level so that during the night time, when you don't have solar, the battery can sustain the critical load, the 100% reliability to the critical load. And then, of course, you want to maximize power to the non-controllable load so that you're not always load shedding, or load shedding will be the last thing you want to do, but not always telling your customers to curtail their demand on those non-critical loads. So you want to also maximize customer satisfaction. So you want to make sure that while you supply the critical loads, while ensuring your state of charge on the battery is at an optimal level, while maximizing the usage of renewable energy sources, minimizing the usage of backup generation. It could be diesel and not friendly. You also probably want to think about sustainability from the microgrid point of view and try to minimize importing power from the utility grid. If sustainable, if green energy is the goal of the microgrid, then utilization of renewable energy resources to meet the load will be the preference. So all these objectives are there. At the same time, you do not want to put the effort on the battery to be high such that it degrades its lifetime, right? Minimizes its lifetime. So you can factor all of this into a cost function, right? And solve that for dispatch. So this problem of dispatch happens with all these objectives. If you're able to do that, then of course you have a self-sustainable, reliable, environmentally friendly, and technology-ready microgrid, right? So how do we do this, right? One way to do that would be to go through sorry, I don't have a decision tree here, but to do that would be a decision tree to, you can implement, that's the traditional way of saying, implementing microgrid control, this rule-based approach, right? But you can't solve all this objective using a decision tree. And even if you did that, it will be static. Okay, how do you develop a dynamic approach? And then you go to this adaptive critics that I talked about, and you can formulate all those objectives into a mathematical function known as the utility function. And you can have different weightings for each of those objectives depending on your priority. And that utility function can be learned by the critic to come up with the cost to go function J, which is the Bellman's equation of dynamic programming, right? And that's a forward-looking network. So that is telling you, let's say this microgrid dispatches every minute. This forward-critical network can be designed to look ahead 10 minutes or 30 minutes or 1 hour accordingly, and provide feedback to the controller through a derivative signal. And you can learn this from data. So you can design a microgrid today, a microgrid controller today, but the weather might be different 2 years from now. And using this method, the controller evolves with the changing conditions. So, if you have solar, wind, then that's going to change. If you have loads, that is going to change. This controller is intelligent because it adapts with the changing conditions and still maintains that performance, right? So that's the approach we used here. And of course, some 2 days of data here, wind and solar, the load, critical load and controllable load. And you can see the priority controller is the decision tree-based controller, and the blue line here is the intelligent controller using adaptive critics. Both of them, because the critical load is top priority, and both are able to meet their critical load. But when it comes to the controllable load, you can see that the red line, the decision tree, is dropping the transition on and off of the non-controllable load is very abrupt. It turns it on and turns it off like bang, bang. whereas the intelligent controller can foresee and does those transition in a smoother way. Okay. Also on the battery, we have a deep discharge with the priority controller, whereas with the intelligent controller, the discharge is not too deep, so it looks at the life of the battery. So in terms of performance index, we formulated two matrices here, two indices. And basically what these indices are looking at is two things. One, an indication of how much of renewable energy was utilized to meet the load demand. If you can use just only the renewable energy to meet all of the load demand, and that will be the best, right? That means you're not turning on your backup generation or you're not importing from the utility grid. The other thing is how much of the controllable load was met. If you met all of the controllable load, that means you didn't put your customers through load curtailing or demand response. You met all of the load, right? So ideally, the best performance would be you met all of the load from renewables. That would be the best scenario. Okay, so that means if this index is 1, that's the best. Okay, of course, you can design the microgrid such that it comes up with a 1 by putting large amount of renewable energy sources that exceeds the load, right? Such that you can do the calculations and install, but then the cost will be high to do that. The second one is looking at the energy life of the battery, and we factor that into it. How many times it's changing the status of the battery from charge to discharge and how frequently. We do not want to frequently go charge, discharge like that. So we want to find the best way, how many minutes should it be on charge and then discharge depending on what SOC is, and factor that into the index as well. And if we are able to, after factoring that, we're able to get 1, then that's the best considering the life of the battery. So here's an interesting result we have. So the normalized PI is basically comparing the performance index with the DEMS, the intelligent AI approach, with respect to the decision tree, traditional priority controller. So we can clearly see that it's above 1, which tells us that the AI controller is better than the decision tree-based approach. What's even interesting is that now we did the study for different SOC level of the battery, 30% all the way to 100%. And also we looked at different battery size from all the way from 2,000 to 10,000 kilowatt hour minutes for a given microgrid that we designed. You will see here, if you maintain the SOC at a certain level, around 55 or 60% around there, and then you have the right size of the battery, you can get almost 30% more of PI for while maintaining that SOC and that battery size just by using the AI approach. Okay, so how you maintain the SOC matters, right? That is the dispatch, is the intelligent dispatch. And you don't need a bigger battery to do that. You just need the right size of the battery to do that, right? And this is using adaptive critics. So the two things you can take from this. One, you can design a microgrid and use this adaptive critics approach to get 30% enhanced performance. Or you can design the microgrid to a smaller size and get the same performance. So that means less capital. Okay, so those are the two ways you can do that. And all this just comes because how you do the dispatch. Okay, the adapter, the actor, the optimal control policy. That was my first example. The second example is going to the power system. This is the New England, New York power system, which has about 16 generators, 5-area system. The problem we are trying to do here is just to identify the generator dynamics, okay? And the generator dynamics here is all the 16 generators from the speed or the power outputs of the generators, we can pick up the electromechanical oscillations in the system, right? So we use the CCN to model this and cellular computational network. So since we are interested in the electromechanical oscillations of the generators, 16 generators, so we have 16 cells. And if each cell is connected to 2 other cells, this is how it looks, and it is a divided system. So this tells us that in some cases, some of the cells need to have more than 2 neighbor connections. And if we extend that to 3, we have the complete New York, New England system in the cyberspace with 16 cells. So now each of the cells, basically in this problem, the way we solve it, has a simple feed-forward or recurrent neural network, but they're very small, compact neural networks, okay? And we are able to identify the speed deviations during disturbance. I'm just showing you a sample of the generators here, 6 out of the 16. The PMU output, the PMU output is the blue line, and the dashed red line is the output of the cell that's predicted. This is predicted, which means it's ahead of time. Okay, and we did the model analysis to pick up the frequency and the damping in each of this. And the black one is from the PMU measurements, the actual measurements. And the one in the orange is the one from the cell, what the CCN graphs, we analyze those. And you can see they're almost pretty close here. Okay, the modes have been picked up by the CCN, what exists in these waveforms. And I'm just showing you for generator 3, but it is for all the generators we're able to do that. What's interesting is that, let's, for example, focus on generator 10, which is modeled by C10. And C10 is connected to C12, C11, C1, and C14. C11 and C12 are in the New York area. C1 is in the New England area, so we have inter-area, and C14 is in another area 5, so you have inter-area dynamics there. So if I cut this, I get a subgraph that looks like this. So the emphasis is on generator 10. It's connected to 4 other cells. So all of this data comes from PMUs. So all the 16 generator substations are PMUs, and they're transmitting at 30 hertz data to a control center. And at the control center, we can develop the model of C10. So this is how C10 will look like. And if the C10 neural network will look like something like this, basically all the data coming from all these neighboring cells, and then that's what we are predicting. So also we have a recurrence. There's a connection from PMU 10, PMU 11, PMU 12, PMU 1, and PMU 14. So 5 PMUs are connected to get this output at the control center. So 5 sensors, 5 IoTs. And I think I talked about the vulnerability that if you have more of this networked devices, any of those devices, for one or more reasons, it could be a cyber attack, or it could be a communication problem, and you could lose that data for some period of time, depending on what kind of problem it is, right? So let's say C10 and C1 PMUs, for some reason, are not able to send across that data, the 30 hertz measurement, okay? And then let's say after that, to make it even more critical, let's say now PMU 11 also fails for some reason. Okay? And even to make it worse, let's say now PMU 12 joins that group of failure. And then finally, PMU 4. That means now we have 5 PMUs, and let's say in sequence, all 5 PMUs went out. Okay? Can the cell 10 still predict the generator 10's output? Okay, that's the problem here. So all the PMUs are IoTs. Now question is, can we create intelligence through virtual IoTs? Okay, that means they don't exist in reality, but can we create them virtually? So here, the first attack was 2 PMUs are out. And here one sample is 3 PMU data samples, and it's 100 milliseconds. PMU sampled at 30 hertz, each is 33.33 milliseconds. So this is 3 samples of PMU, 100 milliseconds. You can see the PMU data that would have actually been is the blue line, and the predicted one is the red one. Okay. Now, 3 out of 5 PMUs went out, and you can see the blue and the red. 4 out of 5, 5 out of 5 for one sample, 100 milliseconds. Okay. Still, we get a very decent gradients and prediction there from the cell 10. What if that time went from 100 milliseconds to 500 milliseconds? With 5 PMUs out, we still can get that. What if we went from 5 samples, 500 milliseconds, to 1 second? You can still get a decent prediction. What if we went to 2 seconds? Of course, this has degraded to compare to this, but still it's able to predict the gradients, right? So we have created virtual intelligence, virtual PMUs, virtual IoTs through the CCN. Okay, so that is the coolest benefit of creating a CCN, distributed intelligence. It's like you knock out one of your ground agents, you don't lose intelligence, you still have intelligence, okay? So distributed intelligence, right? You're not dependent on one, but you have several, and then part of the group is out, but the rest of the group is still there. If you still remember, we have 16 PMUs, right? Because there's 16 generators. I only knocked out 5. That means the remaining 11 are providing the intelligence, right? That's how we solved it, right? Okay, so I've just shown you on how to do this for electromechanical oscillation detection of the generators, but we can extend this to do much more than just one variable. We can look at the voltages at every bus. We can look at all the generator power outputs. We can look at the line flows. We can take that into transient stability margin calculations, voltage stability margins, and then even control. Okay, the top is open here for the CCN. You can have multiple layers. Okay, so it all depends on what you want to put in there. You can develop that. Here we have we did this on the TransPower, which is TransPower, as many of you, or some of you may know, it's for the New Zealand utility. South Island, this is South Island power system. And here we have a load center Islington. And I'm going to throw a fault on the Islington bus, load bus. And we're going to see how the CCN is able to predict all these different variables. Here we have the voltage variation across the island, the frequency variation across the island, the power and the different generators of the buses, and the transient stability margin. And here is the line flow on one of the lines on this network. Right now it is 0.71 per unit, even though it's changing, but it's still 0.71. The fault is going to happen anytime now, and you're going to see how through the CCN we model all these different variables, dynamics happening on the grid. Now it's happening, the fault came in, boom, and you can see how the whole island goes through the frequency variation, the voltage fluctuation. Yeah, so with the CCN, with the cells, it's easy to build and even implement this on a computing machine, because you can parallelize this nicely. Every cell is basically can be on a processor, and all of this works together nicely in harmony, and eventually you can capture all the dynamics you need to Once it settles, it's basically going to settle, and then it comes back to normality, and everything returns to state of the normal state. So that's the beauty of the CCN. It's highly scalable, okay, easy to implement, and gives you immediately the impact of a disturbance right away. So my third application and last application for today will be on how we even took this further to when a PMU is attacked. I showed you that we can have virtual IoTs, virtual PMU, and AGC. Many of you might know automatic generation control is important for frequency control. So here's a two-area power system. We have AGC1 with feedback of frequency taken from PMU7, AGC2 feedback of frequency taken from PMU9. So it's a two-area four-machine power system. There's a tie line flow. So AGC1 does tie line bias control. So in addition to the frequency control, it also ensures that the tie line power flow, whatever the transfer, is also maintained by AGC1. Okay, so you can think that definitely PMU7 is going to be very critical since it's doing a tie line bias control. So in the lab, we modeled not only the power system, but also the entire communication network. So all the security gateways and all the switches, all the data flow, basically, all that have been modeled in real time on the RTDS, real-time digital simulator. And we also have a 210 megawatt PV plant. And also this PV plant is dynamic in the sense that this is done at Clemson. So we use the Clemson weather, solar irradiance, to power the simulation of the PV plant. So if there's a cloud cover over the lab, the production of the PV plant will drop. And if you had great 100,000, 900 watts per meter square irradiance, then it will be like 180 megawatts production of this plant. So it changes with the cloud. So we can do a real-time simulation, truly real-time, without having a 210 megawatt PV plant. It's modeled, but driven by the actual weather. Interestingly enough, we did the 2017 August, I forget, 21st solar eclipse study at Clemson when we had the darkness for I think about a little over 2 minutes. So we ran the simulation of the large renewable plant, what would happen under the solar eclipse study, so using a similar idea of using the irradiance. And yeah, so it was interesting to see how AI technologies handle that compared to the traditional AGC methods. So I'm going to show an attack on PMU7 while there is a fault happening on bus 8. Okay. Usually cyber attacks will happen, the attackers will disguise themselves under a fault. When there's a fault in the system, that's when an attack would happen, so that the system operators won't know, was it a fault or was it an attack? So we're going to do both here. There's a fault, and then we're going to attack PMU7. Okay, so when we do that, what we see is without an attack, with just the fault, it would have been the blue line. Okay, that means the system will go into oscillation and then it will come back. But with the attack and the fault, it will basically, you drive that to an unsustained oscillation and basically collapse the system. You can see the frequency would just go out. Yeah. There was no countermeasure for the attack here. So our goal was this is 100 packets blocked. That means 100 packets of the frequency feedback signal. That means for 100 packets, there was no visibility of the frequency at bus 7. So we designed our CCN technology, which is distributed AI. So using the same concept that I explained to you about the virtual IoT, which is a distributed AI approach, now we are able to estimate frequency at every bus using the CCN. So we have a virtual frequency measurement, yeah, so to say. So it's all through predictive estimation, and you can see our prediction is really on spot with the actual frequency measurement. That's what we see here. We have paper on this. So all the details of how to do this, it's reported in the paper, and I'll be glad to share that with anybody who's interested to read. So we developed the countermeasure, and the countermeasure here are two different countermeasures. I worked with one of the, and in my department, I have a colleague who is an expert in cybersecurity. He does Department of Defense cybersecurity work. And he says, why don't we just use the loss frequency measured as a feedback? And that is the countermeasure A, and compare that with the CCN countermeasure B. And that's what we did here. So what I'm showing you here is the amount of energy change as a result of the attack from the, in this case, the tie line flow. Because see, the tie line bias control is supposed to maintain a certain power transfer from one area to the other. So this is the deviation of the power transfer agreed to, okay, delta E in megawatt hours. Okay, and this is showing just number of packets lost. So 1 packet, 4 packets, very short interval. Okay, and you can see with no countermeasure that just starts growing. With all these different countermeasures, it's almost like still okay. But when that number of packet grows, the time of the duration from 0 to 600, you can see both the other countermeasures, countermeasure A, case 1 and case 2, just the amount of energy deviation grows linearly here. But whereas with the CCN, it's seamless with nothing. Okay? Because we use the concept, as I explained earlier, virtual IoT, and it still have a frequency estimation. Okay, and without the attack, you can see the blue line. With the attack and our countermeasure, you can see the orange line. So that means with the CCN, it looks like there was no attack, but there was an attack behind the scenes. Right? We can handle the attacks with the CCN because we are doing the frequency estimation using the CCN. It's a virtual sensor, right? It's a backup, it's intelligence. This is the lab. Dr. Age, Professor Age has visited the lab where we do all these experiments. This is a control center, mock-up control center we have put together. We call it the Situational Intelligence Lab. This is the grid simulation lab with the RTDS and the PMUs. All these PMUs are the hardware PMUs that we have. The weather station where we pick up the solar irradiance and bring that into the simulation. Yep. So with that, I'd like to summarize. I know I took quite a bit of time here. I think the message to take home is distributed intelligence. Okay. I think many are working in AI, but I think it's important to work in distributed AI. Distributed intelligence is the only way to, I see as for scalability. And cellular computational network, which I've introduced to you, is one way to break down the complexity without losing the coupling affinity. And that way we can have scalable AI. And to truly develop intelligent machines for the electric power system or the modern electric power system, we need CSTMs, computational systems thinking machine. Thank you for your attention, and I'll be glad to take any questions, comments, both here in person and both online, if anybody would like to ask. Thank you. Yeah, they say online. Oh, okay, there's a clap, I think. There's a clap. Thank you. Something on the chat, but yeah. Yes, so whoever has a question, I think if you can speak up I'm not sure whether the audio has been joined there because join audio doesn't seem to be joined.
Okay. Can you please
It doesn't seem like the audio is
put
connected.
his hand up?
Yeah. Ah, Logan.
Hi, Logan. You online?
Oh, hi, Prof. Long time.
Yes, Logan. How are you doing? Good
Yes,
to see you.
no, good, man. Good. I'm glad you're looking very good.
Thank you.
Yeah. No, one
You
of the
as
things
well.
I wanted to ask is, we're doing a little bit of work on blockchain and Web3. And I mean, I think all of these developments, in the internet was because of the TCP IP, that almost Jim Berners-Lee gave it for nothing. But there's now the talk of Web3 being a blockchain-enabled web. It gives a lot of advantages to security and all of that. But have you looked at the maturity of the technology, for adoption in the power section or the power? Because in the power area, we struggle with what we call operational technology and then information technology.
Yes.
The way I see it is Web3 is going to probably bring these things closer together. Have you done any work on that?
So we are looking at blockchain currently. That's one of the things definitely for power system security in terms of IT. That's important. So I have not presented anything today on that, but yes, we are looking at blockchain for power system security, IT.
No, great. We can have more discussions. Thanks a lot for that.
Sure, you're welcome.
The question here, just regarding, have you commercialized these ideas and patented what is resulted from those research?
Yeah, I think you probably need to say that through a microphone for the sake of online.
So, Kumar, just wondering, all this research, has it resulted in any commercialization and patents?
Yeah. So, yeah, some of the ideas have been patented in the United States. So, yeah, the C10 technology is a patented technology. Yeah. So, so we are in the process of we are working on projects that in the US. One of the things we have is the technology transfer, the innovation funding. So we are working with industries, utilities, to vendors to take some of this to market. Yeah, so that's in the pipeline. Yes.
Any other questions? I know yeah.
Thank you, Prof, for that lovely presentation.
You're welcome.
I just have a question around the utility of the future and what your view around that would be. So how should utilities be upgrading their steady state SCADA systems, for example, to gear their operational capabilities for the future smart grid? What are your perspectives around that? And what are the trends that you are seeing?
Yeah, so definitely, I think it's very important that the more sensors we put in, the more granular resolution we get, right? And I think there's an optimal point how many sensors we should have so that we can get the maximum performance. Again, investing into the transmission phasor measurement units. Now you also have micro PMUs for the distribution systems, and of course you have smart meters, and the micro PMUs are much faster measurement devices, using smart meters to get data from your customers too. And of course, smart meters can also be put on a faster sampling. So it's all about when you put all these devices that you get data, do you have the technology also to process the data and make sense of the data, right? That's important too. So definitely as we look at the future, utilities should look at keeping the eyes open, if I may use that, eyes through the sensors on what's happening on the grid, because if the grid is going to become more distributed in terms of generation, right? So a lot of the distribution systems are going to have generation. So you need to have, in order to maintain optimal power flow, security, you need to have these measurements at a faster rate and be able to process it and monitor it and control it, right? Optimize it, right? So that's important. And I think the utility of the future has to get more digital. It's more digitalization of the grid, right? Yeah, so at the same time, not only from a technology, operational point of view, but also from the enterprise point of view too. You have to look at the utilities of the future has to look at different business models, right? How do you now, as I said, one of my 7 bullets of the smart grid, clients, right? So the consumers are now clients. So what are the new business models? Because utility of the future is not going to be the utility of today, right? When it comes to 2050, we are seeing a whole different utility. So if utilities have to stay in business, then new business models will be important, right? So I think a lot of it, it's going to be quite interesting and challenging for the utility, the power industry. So an exciting time, but yeah, of course, situational intelligence in planning is important, right? To see that, and yeah, because customers are going to be really active. They're going to be, consumers are going to be active, right? Active distribution, active consumers as prosumers, right? So there'll be so many distributed, the power system, the centralized power system will become more and more distributed. So when it's distributed power system, and still one power system, because there'll be times when the backbone is the utility grid, right? When you don't have your localized generation, because a lot of local generation will be there, right? So there's a whole transformation, right? Yeah, yes, you're welcome.
On that note, I'm very mindful of the fact that we've kept you there for over an hour and a half.
Oh, that's okay.
Let's ask John
That's fine.
to please, if you kindly close the seminar. Thank you.
Sorry, missing the. Okay, so all right. Good afternoon, everyone. I think let's give one more clap for sharing with us some of his latest thinking in smart grid technologies and how they are evolving and what they are contributing at their institution. I think we are happy and proud. You have some of your roots here.
Yes.
And you've always been here persistently with us. I met you here with Prof. Davidson, Prof. Dore, and Dr. Lee.
Yes.
So we thank you for being here with us. And we trust that you will be here with us for a long time.
Yeah, thank you.
All right, thank you very much. It's disadvantage for me. Let me not speak much and discolor all the great things he has said. But I think there's, for us to set our thinking, what can we take away? What can we translate into our research ideas? I know online it's a lot of people from ESCOM. What can inform the evolution of ESCOM their colleagues also from Etequini municipality. I wish to recognize you. My good friend, we've parted ways for some time, but we're still together. But I think we've all seen new opportunities and new directions of how we can make a difference and improve. So I thank you once again. Thank you, Lee, for giving us the opportunity. I think it was brutal just to lay hold of you and say, can you do this for us? And you stood up and you raised your hand, and you've done it for us. Andrew, thank you. We've not seen what you've been doing, but I know that you've done a lot to get us to this point. My colleague, Dr. Khan, is here. I may not recall every name. And for you online, we can't see all of you, but we want to thank you all for making your time to attend. And we got some very good contributions from there. So thank you all. Thank you to the technical team. We are grateful for all that you've put in to get this to the success we have seen today. And I appreciate all of you. I think at this point, we may be bringing the meeting to a close. I don't know if you have some announcement. It's okay. So once again, thank you all. And let's remove the presenter to his seat nicely with another clap. We can step down, except if there are a few comments here and there. Okay, so there's some tea and snacks. Well prepared. Let's make sure we take very good care of them once we walk out of the hall. Thank you all once again. Bye.